Yes. So I welcome everyone and welcome you to our next webinar in our series of webinars related to our ATENA software. So let me summarize the rules of our webinar. So please have your microphone turned off. Of course, you can turn on your camera, maybe at least at the beginning, if you like. It is always nice to see that we have some real persons and real faces behind on the next part of the optical line, yes, optical fiber. But anyway, and later on, maybe you can turn off the camera so we have good connection for everyone. And if you have any question, then I recommend that you use the chat window at the bottom. There is you can click on the chat window button and you can type your question there. So please do not wait till the end. Type your question anytime. And Drahoš, who will be presenting today, Professor Novak, who will be presenting, I recommend that you activate the chat window. I'm not sure if you know how to do it, but at the bottom there is this chat. And if you click on that, it will open it on your screen so that you can see what are the questions there. And from time to time, it would be good if you look at this chat box and stop your presentation and answer the questions. Were you able, Drahoš, to open it?
Well. So I'm now already shared the screen. So.
But still, if you go at the top, if you move your mouse to the top of your screen, then kind of a menu comes out.
Right?
I'm sorry?
Conversation.
Probably, yes.
It's probably there, yeah? Okay.
And then you can see a small window, and if I type something there, like I'm typing.
Yeah, I see. Okay, it's there, yeah.
Yeah, okay. So I will start recording. So I am now. Oh, okay. It's actually already recorded. Yes. Okay. So the session is automatically recorded as it started. Okay. So with this, I would like to transfer the presentation or the word to Professor Novak from Technical University of Brno, with whom we are cooperating from Červenka Consulting and ATENA software, mainly in the development of the probabilistic modules and capabilities in ATENA. And he will talk about the probabilistic analysis in general, and specifically about the FReET software. For those of you who have used SARA software together with ATENA, you probably noticed that as a part of this SARA system, important part of this SARA system is the FReET software. So please, Drahoš, I give you the word, and please continue. So.
Okay, so thanks a lot, Jan, for a nice introduction. Hello, everybody, and I am happy to deliver some short talk here in this type of the webinar. And my talk will be divided in two parts. About 30 minutes will be PowerPoint presentation about reliability, which is implemented in FReET software. And second part, the next 30 minutes will be just, let's say, live demonstration of FReET software using a relatively simple example. I am coming from Faculty of Civil Engineering, Institute of Structure Mechanics, Brno University of Technology in Czech Republic, and as Jan mentioned, our reliability group cooperates with Červenka Consulting more than 10 years on developing of probabilistic engine, right? So First of all, motivation for that. So we know that uncertainties are actually involved in every part of the system structural environment, and that's probabilistic assessment of engineering system is needed. Generally, random response Z is a function of basic random variables or random fields X. So that is function of the X, where function Gx represents a compression model. And this compression model can be relatively simple or quite very complicated. So actually 3D nonlinear fracture mechanics compression model is relatively complicated, but we need still to play with uncertainties. We usually distinguish three types of analysis. One analysis is statistical analysis. So we are interested in, let's say, mean value of the ultimate capacity, variability of the deflection of the bridge, etc., right? According to this formula. Then reliability analysis, if the function itself represents safety margin, that it's a failure when function is negative, then we are interested in calculation of probability of the failure, probability that the function is negative. And another type analysis is sensitivity analysis, which is quite important, which can distinguish between dominating and non-dominating random variable and quantify importance of random variable in our problem. Well, we deal with computationally intensive problem like nonlinear finite element technique. So the techniques developed for that should be quite efficient. Usually such approach is called uncertainty quantification. The quantity of interest of physical system is represented by some mathematical model, right? And we have to assume uncertain input variables which are described by specific probability distribution function for material, load, geometry, etc. And uncertainty quantification of the characteristic means that we need to assess statistical moments, probability distribution function, etc. of some output. So there is a model, and uncertainties are just on the input, and we propagate the uncertainties through the model to assess the influence of uncertainty on moments, probability distribution function, sensitivity, etc. So this is just brief explanation of what is called uncertainty propagation, uncertainty quantification, right? Well, just to attract your attention, I just present, let's say, the aim is reliability estimation. So long time ago, we calculated this called the Hierarchical Bridge on Brenner Highway, Italy. And we deliver with a picture of the safety index versus level of the line load for different coefficient of variation, and we compared with Eurocode 4.7 description, right? And failure probability is actually, or reliability index is time dependent, and to get such a picture, we have to work with several things. Of course, the first dominating thing is to have really good compression model, which in this case was the model in ATENA, and you can see the failure of the bridge due to uncertainties. It failed approximately in 60% in bending, in 40% in shear, and it was the influence of uncertainty. So a good compression model is needed. There was here a lot of restricting strength, etc. After deterministic model has been set up, so we need to make stochastic model. So it means all parameters should be considered as for concrete, for reinforcement, for plasticine steel, should be considered as a random variables with probability distribution and the statistics, right? So This is just example, which I would like to emphasize what is needed to calculate the reliability of such a bridge. Of course, we need to have good knowledge of material parameters, of testing or laboratory or in situ. We need to use efficient small sample uncertainties simulation technique, which we implemented in software FReET, and combined with advanced finite element nonlinear analysis and material models in software ATENA. Actually, you are mainly user of ATENA, so you know what I am talking about it. Last but not least, our structures degrade, and so we need to model degradation. So we developed also some special module of software FReET where 50 degradation models are implemented. Okay, outline of my presentation will be, I will mention something about small sample analysis, about uncertainty simulation by stratified sampling technique, hierarchical sampling, how we work with statistical correlation among random variables, and I will present FReET software for statistical sensitivity and reliability analysis. Just as a part of the SARA system, which is combination of ATENA, FReET, and possibly also FReET-D. This combination will be presented actually in 2 weeks by colleague from Hierarchical Consulting, Dr. Cooper. So I will do some software demonstration of the FReET. So my task is today just to inform you about the FReET software and the basics. Some introductory remarks from reliability theory. We usually work with safety margin, where limit state function is a vector of basic random variables. It can be explicit or implicit function of basic random variables, and it's very simple or very complicated. And basic reliability condition is if the safety margin is negative, it means the failure. And if it's a positive, we are in safe region. Like in this two-dimensional case, somewhere here is a probability distribution function, 2 random variables, and it is the space where the function is negative, right? And we need to calculate it. The basic measures from reliability engineering are failure probabilities and reliability index. So in case of failure probability, it means that we need to calculate probability that the function is a negative. So in integral form, it's actually integral over the failure domain from marginal probability distribution, possibly correlated, right? And if we represent safety margin in original space here, so we have a mean value here, and integral from -infinity to 0 is a failure probability, and failure and safety index represent how many times we put standard deviation of the safety margin between 0 and the mean value. So this is original space of safety margin. In case of the ATENA, we can for example simulate ultimate capacity of the bridge, for example, and combined with the load, and it's the safety margin. If in the case that we do normalization, standardization in statistical case, so then we switch to normalized space, and reliability index beta is just this distance, and failure probability is a distribution function for minus beta. I really cannot go in very detail, so I will be just on the surface. But simple cases of safety margin is usually separation of safety margin in 2 parts, in resistance and the action of the load. This is actually in Eurocode, and you can imagine that resistance is a strength, action of the load is maximum stress, resistance can be allowed deflection, action of the load is deflection, etc. It can be different types. So, And if you represent the both quantities are random, right? So that's why influence of uncertainty propagation means that we arrive to probability distribution function of the action of the load and probability distribution of the resistance. And in connection with ATENA calculation, when we perform uncertainty propagation, we obtain probability distribution of the resistance, which is obtained from ATENA. So this is this red here, and then we combine it with the load, right? So concerning uncertainty simulation, we use very efficient small sample simulation technique of Monte Carlo type, which is Hierarchical Sampling. Every random variables is divided in n simulation strata layers, and each layer is used just once in simulation process. Okay, so that you can see that the realization covered random variables very well, very efficiently, even using small numbers of the simulation. Selection of realization from distribution function is done according to this formula, which is actually centroid of the layers. And because we produce random variables from the centroid, so the mean value is consisted of centroids, and it's reproduced absolutely precisely. So this is the most efficient technique of stratified sampling available, which was invented by Huntington and Virincis. And we need that because very often we can allow only tens or hundreds simulations, not more, which is quite small number in reliability engineering, right? So, as I mentioned, in uncertainty propagation, sample averages equals exactly to the mean values of the variables, and variances of the sample are set much closer to target values compared to classical Monte Carlo technique. So, and for most distribution, integral can be solved analytically, but these are just numerical things behind, not necessary to say. Well, in our case, when we work, for example, with the concrete properties, compressive strength, tensile strength, fracture energy, modulus of elasticity, these quantities are statistically correlated with some prescribed correlation coefficients, right? And we have to impose this statistical correlation, otherwise we are wrong. We are not reproducing the nature, right? And in our software, we implemented very efficient technique which we invented based on simulated annealing approach, where this is a simulation scheme. This is a simulation scheme. In rows there are realizations. In columns there are random variables, right? And if we make switch between realizations, we influence correlation matrix. So that's why we define the optimization problem in such a way, prescribed correlation matrix minus generated, and we need to have this difference as small as possible. It's possible to do by force, but it's not very efficient. So simulated annealing approach is much better, and it works in such a way that we impose some probability of escaping from the local minima to get global minima. So this technique appears to us very, very robust actually. It has some mathematical feature behind, and usually user of the FReET it's not necessary to know details for user because it's very, very robust, and usually default values for this imposing is not necessary to set up. So, well, we also implemented in case of hypercube sampling, so-called hierarchical sampling, because in case of stratified hypercube sampling, it is necessary to specify the number of simulations in advance, right? and you cannot add the number simulation freely, like in case of Monte Carlo. So it looks like a disadvantage. So that's we developed the technique of hierarchical sampling, which works in some kind of cascade sampling, and it's possible to add number of the simulations step by step, also in this efficient technique. Sensitivity analysis. Sensitivity analysis is additional product of high group sampling simulation, right? And it used the non-parametric rank order correlation between input variables and output response variable. So we have, for example, here in this table, you can see simulation and you can see variable X, variable Y, and some result, reflection of the beam, for example. And we are interested how much variable X influence G, how much variable Y influence the G. So instead of absolute values, we switch to orders, to the ranks, and then we calculate non-parametric random correlation, statistic like Kendall tau or Spearman correlation coefficients between let's say first variable and result, and between second variable and the result. Bigger correlation coefficients mean higher sensitivity, and it can be in both positive and negative sense. So if we get, let's say, coefficient of correlation 0.8, we know that the variable influence the reflection quite a lot. If we get 0.1, so it's not so much. If we get minus 0.7, so it influences quite significantly, but in negative value. So it means bigger variables, smaller result. So it's relatively easy sensitivity analysis. Actually, nowadays there are a lot of sensitivity analysis which our group are also working, but we don't have time for that. In case of reliability analysis, we very often use simplified rough estimates, as we are constrained by extremely small number simulation, tens and hundreds, and for such small number of simulations, right? So to get this contribution, this overlapping point in the safety margin is quite difficult. So that's why we used simplified estimate, which means Cornell safety index based on the Gaussian distribution of safety margin and the statistics only. Also by curve fitting, we implemented also first order reliability technique, and we are working with surface too. I talked about random variable approach, but some time ago we also did some research on influence of randomness at the level of random fields, which is random fields represent the random distribution of material properties along the structure, so it reflects spatial variability. So for example, here you can see 2D structure and some random field of some properties, compressive strength, fracture energy. It's here, it's C, and then you amplify the weak points in the structure, and then crack patterns corresponding to that in ATENA modeling, in fracture mechanics are different, and also horizontal straits corresponding. But this is really advanced topic which needs separate lecture, but I only mention because of complexity of the picture. So, as a probabilistic engine, we developed software which is called FReET. It's a multi-purpose probabilistic software for statistical sensitivity and reliability analysis of engineering problems. It allows to simulate uncertainties of the problem at random variable level, typically in civil mechanical engineering, material properties, loading, etc. Right? Actually, it was first developed for randomization of the ATENA. it's also some of our users are using it as a standalone program for other purposes, right? So there are two versions of that. So these are windows of the FReET software. You can see here, let's say that there is a tree window where you operate the software. Here is a let's say communication window where you type your input data, and here is a picture window where you see what is an input or result, right? So first of all, a random variables window. It has friendly graphical user environment here, and we can use about more than 30 probability distribution functions, mostly 2-parametric, some of them 3-parametric, like Weibull distribution, some of them even 4-parametric distributions, like beta, very flexible probability distributions. Unified description of random variables with optional use of statistical moments or statistical parameters, or combination of moments and parameters. And so there is more also probability distribution function calculator, where you can let's say play with this input the data and then modify that it's relatively user friendly. Then there is a statistical correlation window where you can prescribe the level of statistical correlation, and actually the software also check if the correlation matrix is positive definite or not. It should be positive definite, but it's another story behind, right? And the limit state response function window has several possibilities. There is a closed form direct implementation of response or limit state function using implemented equation editor, right? Then based on input random variable, you put the function here. Indirectly, there is a DLL function prepared in any programming languages, and there is a general interface to third-party software using BAT or exe programs, which need some programming, right? But in case of ATENA, so this interface to ATENA is developed very well to very good user-friendly environment called SARA, and transformation between data between ATENA and FReET, and from FReET back to ATENA is done in a very easy way. So user of the FReET software with ATENA under SARA software cannot let's say, or not necessary to take care about this indirect definition of the limit state function. But it will be in 2 weeks by my colleague Radomir. So reliability window after Monte Carlo type simulation, there is a histogram of output variables, right? And you can see sensitivity measures, reliability estimates by variety of techniques, also some parametric studies can be done, etc. So in software, there are following probabilistic techniques implemented. There is a crude Monte Carlo simulation, Latin-Hard sampling in 3 alternatives, hierarchical sampling, approximation technique, first order reliability method, care-fitting technique, simulated annealing for correlation control, and also Bayesian updating. If you have some real measurement, you can combine it with let's say a priori estimation by a stochastic model to combine with posteriori measurement to get posteriori estimates. Okay, just one word about FReET D module. As I mentioned, we accumulated a lot of models for carbonation, chloride ingress, reinforcement corrosion, sulfide, acid, and frost attack under the umbrella of special FReET software. And in such a way, we can make degradation modeling of newly designed or mainly existing concrete structure, and to make time-dependent estimation. This probabilistic engine, as I mentioned, FReET, is combined with ATENA software under so-called SARA software, SARA environment, which is acronym for structure analysis and structure analysis and reliability assessment software. And then this interface is out of the print. But my task now is to explain the basics of the software FReET. And I think that the best is to run, let's say, a real-time demonstration of the software. Because of very, very limited time, I will show the software using really very, very simple example. Imagine that you have some bar in tension, for example, and the limit state function is just resistance minus action of the load. Okay? So, just two random variables, right? Both random variables has Gaussian normal probability distribution. Resistance has 200 units, doesn't matter, or whatever, newtons. Action of the load 150. And standard deviation in case of resistance is 20. And standard deviation in case of action of load is 30. And I will show you working with the software FReET using this simple example. So, because it's basically the same, and before I start, I only emphasize that actually this R here, this resistance, in case of ATENA modeling, in case of the SARA, can be the function of many, many random variables. Maybe five types of concrete. Every concrete is described by, let's say, 6 random variables, right? Then you have a cover of reinforcement, you have a properties of restricting strength, etc. Okay? So usually in our calculation, we use FReET software in connection with ATENA just to see random variability, to assess the random variability of the resistance. After we get it, then we can proceed with reliability calculation. Okay, so I will finish PowerPoint presentation. It's good, 30 minutes is over. Actually, if you want to know more about what we did, about specific techniques in detail and a lot of application examples and journal papers, so visit our web pages, FReET.cz, where you will see much more. Okay, and now just 1 minute break. 1 minute break, as I should put the FReET software here. Okay, maybe during this break, any question until till now? I don't see in chat nothing. Nothing, so I can continue, right?
No questions. It seems to be everything is clear, so you can continue with the demonstration.
Okay. Okay, so everybody can see the screen of software?
Yes, not now.
Is it there?
No, I don't see it at least.
Maybe you need to click again for to share the screen.
For the share screen again. Aha, okay.
Because I think it was interrupted.
Okay. once again.
Well,
We
now
can see your
we can
desktop.
see screen of your desktop.
Oh yeah, good. And now you see the software, right?
Right. Okay.
Okay.
Perfect.
Good. Yeah. Okay. So when you click on icon of the FReET, so you will see such a okay. So you will see such a screen, and there is a navigation tree somewhere here, right? And I will click on stochastic model definition first, right? So if I click on random variables, right? So then at the bottom there is something like category, variables, distribution support calculation, etc. Right? So first of all, I will click the category. What does it mean, the category? It means in my case, I have only two variables. So I will rename this category as a basic category. But when we developed software FReET for ATENA software, we needed to classify, to distinguish between different sort of the variables. And imagine that there are 100 random variables in ATENA software, and they are transferred to FReET software, let's say in one big vector, one big hill, so it will be not very practical. So that's why we have the category like concrete 1, concrete 2, steel 1, steel 2, etc. Right? And this the definition remains here, right? In my simple example, there will be just basic category, and I will click on now in variable as a new. New variable means that I can define the variable number 1. By clicking, I can rename the variable as a resistance, for example, R, right? Probability distribution function, I can click on normal distribution, Gaussian distribution. There is the picture of Gaussian distribution, right? Descriptor statistical moments, okay. I will put this how much 200 we had, right? And we had standard deviation, I guess 20. 20 means coefficient of variation is standard deviation divided by mean value, which is 20 divided by 200 is 0.1, 10%, right? So, and there are actually other statistics like skewness, kurtosis, which is used for other probability distribution. As you can see, there are a lot of different probability distribution function you can work with. Of course, log normal distribution, very often used because log normal distribution starts in 0, finish in 0. Gaussian is going to minus infinity, right? Well, in case of the failure of the material, Weibull distribution is very, very popular, right? There are some exotic distributions like triangle distribution, but this is quite good. You see that in case of the combination of the input data is not correct to define distribution, then there is a status error, right? So software will let's say software will block you not to use the correct description of the distribution. Very exotic distribution is half normal, for example. Classical distribution is rectangular, for example, for concrete cover is used, etc. Right? So I think not necessary to go to click all these distributions. So I will go back to Gaussian distribution. I will show you now maybe distribution support calculation. If I click on details, so then there is something like statistical software characteristic where you have your probability distribution, you have the moments, you have also parameters and combination of moment parameters which can be useful for sometimes, and also you can calculate over this distribution some percentile, quantiles, etc., and transformation. But this is no time for that now. There is also possibility to work with raw data. If I click on new random variable and, for example, click on raw data, I can calculate, I can extract them from the file, or I can generate some data, right? Some data, and based on this data, statistics are calculated, and I can apply this empirical distribution for my calculation if I have really raw measured data. Well, now I just delete these random variables, and I would like to proceed with another new variable which we have here. So it's action of the load. It's again Gaussian distribution, right? And it's 150. I think it was 30 probability distribution, and so coefficient of variation is 0.2, right? I can also switch with the plotting of the distribution to cumulative distribution function and to probability distribution function. So I define these two random variables, right? Then I click to stochastic correlation. There is a stochastic correlation matrix. There is a correlation matrix, and optionally, these my variables are not statistically correlated. But if they are, I will put the correlation, right? And this is just the image of correlation matrix. So I will go back. I will go back again, right? And I will do sampling simulations. So general data means that I will now click, for example, 200 200 simulations only, and I will use sampling technique, Hierarchical Sampling mean, which is efficient. These are some data for the simulated annealing, which I will not touch now, and I can make run. There is some information about reaching correlation matrix in case of some non-zero correlation. So there is simulated annealing picture about imposing of the correlation, but at the moment there is nothing like that. Next block is check the samples. Okay, if I check the samples, if I click to resistance, I can see that I have here resistance, right? And I needed 200 mean value and standard deviation requested. So these statistics were obtained very, very well here, right? Also the action of the load, 150, standard deviation 30, obtains 30 to 1 approximately, but these are 200 simulation already, right? If I click on upper or lower diagonal, I see realization of this particular random variables, right? I can also number, so this is simulation number 1, simulation number 2, etc. So I can see it, right? and it's just simulation plan, right? Okay. Well, there is a next button is a check variable data. Some of our users actually use the FReET to prepare stochastic realizations only. So these are the columns for resistance and action of the load, and it can be transformed somewhere and to use in, for example, different software. So I will do to model analysis, right? And in case of the model analysis, I should define a new model function, right? Sorry, I clicked twice. And there are two possibilities. One possibility is these three dots means that I implement the DLL function or let's say interface to other program, right? If I click to A to B, so simple calculator appears there. Dr. Pukel will show you in 2 weeks that actually this part is in Sara performed in different automatic way because limit state function is represented by ATENA, right? So it's bind together, and but now I am presenting its standalone module. So function gx, and I can, here are my variables. X1 is a resistance, double click. I will put minus, double click, action of the load, right? And if function is more complicated, I will put divided by 8 plus x2, etc., right? But my function is relatively simple. It's only this one. I have here quite interesting function. The button test. If I click on test, right, then the function is evaluated using the mean values of the variables, right? It's not mean value of the function. It's just calculation of function with mean values. In our case, it's very simple. It's 200 by minus 150, right? But in some cases of more complicated function, this function is very, very useful because you have to know the behavior of the function at deterministic level before you randomize it. And especially our students, for example, they are doing a lot of mistakes with units, for example, and then they have the function g always negative or always positive, so etc. So, and usually they have trouble in the function. So I will keep it. Okay, so I have functions which is defined, right? I will make run model analysis, right? And now 200 random realizations were actually done, and clicking on simulation results on histogram, I can see immediately the histogram of these values, right? And mean value is in this simple case is 50. Standard deviation is about 36. There are coefficient of variation, skewness, kurtosis, minimum, maximum, etc. Right? I am interested in probability that the function is negative, so it means in integral below to 0. So I click on reliability, right? And I can see now the reliability window where it's again mean value, standard deviation, coefficient of variation, corner safety index, which is mean value divided by standard deviation. So it's based on Gaussian distribution. Corner probability, failure probability is here 0.3 to the power of -2, right? And software will also evaluate the best probability distribution available from all these probability distributions based on Kolmogorov mean of test statistics. In this case, the let's say Gaussian minus Gaussian is again Gaussian, as you can see. So it was evaluated very well, and it's the same result as Cornell safety index at some confidence level. Here we have estimation of the failure probability based on let's say definition of the probability. So it means I perform 200 simulations, right? And some of them, so this end total was 200, and some of them were in failure region, right? And this ratio is failure probability, and this estimation has some coefficient of variation, which is here quite big, 0.27% coefficient of variation. If I can check the samples, I can click on this realization and I can click the function itself, and you see here that these realizations here, this red one, they failed in they were in failure region, right? So this green one, they were in safe region. So they divided the space into two parts, safe and failure region. So, and number of these red points divided by the hold points means the failure probability, right? But variability is still quite big. I can easily, in case if I want to increase this estimate, so I will put let's say 1,000 realizations, right? 1,000 realization, which will increase my accuracy. Here I have the same stuff, so 100 points now. So model analysis, run model analysis, so it's very quick. And I can click on reliability, and I can see immediately that my frequency estimation was is 0.4 to the power of minus 2, right? Which is close here to the Gaussian distribution. And let's say coefficient of variation of this probability decreased only to 10%. So it's a much better estimate, right? So then I will show you something else. Let's change the stochastic model in such a ways that, for example, my resistance increased maybe 150, right? I will keep the variability 10%, but the resistance is increased. So it means failure probability should decrease. So again, general data, I will run it very quickly. Examples, you can see it. It's the same model analysis, run model analysis is there, and reliability. I am somewhere here, right? And you see the zero shifted to the left tail, and this content is much smaller, and failure probability is much smaller, right? 7 to the power of minus 3, but you can see we need here still 1,000 simulations. So in many cases we cannot do this estimation. That's why we used Cornell safety index and or k-fitting approach for the estimation. So I artificially change the data, change the stochastic model to let's say my response will be, for example, resistance will be 300, and also, for example, variability of my response will be much small. And now I will show you what will happen. Something will perform general data. I will keep 1000 simulation, run model analysis, and I will see reliability, right? And you can see here that failure probability decreased to quite small level, 2.0 to the power of -5, which is almost to the power of -6 for ultimate limit states according to our code of design of Eurocode, right? Which corner safety estimated that, care fitting estimated that, but nothing was in failure region, okay? Because we didn't have so many simulations. In this case, we can do that because we have simple function. In case of ATENA, we should rely on this probability estimate. So I will show you very artificial, let's say, really a lot of simulation in this case. 100,000, right? 100,000 maybe, yeah. So I read just the playing. So random analysis. So I'm doing 100,000 simulations and calculated reliability, right? So you can see that these estimates are quite okay, but this one is again 1 to the power of -5 is estimated, but variability is enormous because only one point was in the failure region, right? I'm sorry, it takes some time. Maybe I couldn't do show it now. Well, because I want to click on this G1X and okay. And you can see that only this one simulation is in failure region. Next no, right? So I'm going back and okay. There are a lot of different features like you can copy these graphics, copy the table, save graphics to meta file. So you can do some documentation just using copy graphics, copy table, and put it in Word document, for example, or this is saving in meta file. So our protocol possibilities are based just on the copy of this. I think this was more or less. Oh well, I will show also sensitivity analysis. I'm sorry. There were okay. We just used now again simple cases. Otherwise, it will be a little bit stuck. So For example, the window sensitivity analysis is showing us the influence of random variables. So we can see that resistance variable influence the function x with correlation coefficients 0.55. So it's a positive correlation, and there is a positive trend here, right? And variable e, bigger action of the load, smaller the function, right? So it means the correlation coefficient is negative minus 0.8, right? And it has this negative trend. So this is the let's say sensitivity analysis. In this case, we know the role of these two variables very well. But imagine that you have ATENA model with 100 variables. It can be sometimes surprise about the influence, just to quantify the influence of the variables in the task. So, of course, experienced user from Červenka Consulting knows the role of variables, but sometimes in the model it's not easy to say exactly the level of the influence. So from this point of view, sensitivity analysis is useful. Okay, what to show you? What I didn't show. Raw data is there. Maybe I will finish by, there is one window, limit state function definition, and it's actually it's possible to define. It was designed especially for ATENA SARA in such a case that when you have a random response from SARA, then in this button, by this button, you define the limit state function in such a way that you actually put another comparative values to the already calculated values. But these values are put actually in the stochastic model in the button of the comparative values. So, for example, if I put another load, comparative value load, as a new variable here, and this will be, let's say E2, right? It will be another load, for example, load this of maybe Gumbel distribution, right? And another load will have the value of, I don't know, for example 20 with variability 10%, for example. Then I can put it there and go after that to general data, and now I can sample only comparative values only, so it's a run, right? And check variable data. I have also comparative values now the sampled, yeah, and then I can go to limit state function definition, and I can combine the function minus comparative value E2, which is another additional load which I proceed, right? Then look that I didn't do sampling again. So it means because I calculated response already before. So this is very important, especially when you're using ATENA, because to calculate uncertainty propagation using ATENA can take some time usually. So that's why we invented this approach. And then I can see limit state function definition is already there, and reliability is there because I included additional load. So then mean value changed. It was now resistance minus E minus E1, E2, or how I call it. So failure probability increased a little bit. So also here, right? So I understand that it's very fast, very quick, and but I think it was let's say it was quite illustrative. So I will finish with this simple demonstration, because here a full demonstration using, let's say, more elaborated example than this one takes some time, and also the description of reliability techniques needs much more time. So I had to make it in very compressed form. But as I mentioned,
thank you, Rausch. I'm not sure. Have you answered the questions that were in the chat box?
Probably not yet, because I was a little bit, okay.
You got carried away, yes.
Now I should make the screen bigger. How to make it bigger? Oh.
There was one question which says, has the FReET been widely used by industrial companies for concrete durability analysis? That was one question.
Pardon, once again?
Has the FReET been widely used by industrial companies for concrete durability analysis?
Okay. Thanks for this question. So I had just one slide for FReET for degradation widely. I cannot say that it's very widely. We have for FReET we have about it can be almost 100 users, but maybe majority are from academia. Maybe 2/3 are from academia, 1/3 are from industry, right? It's
and the second question is, maybe we go to the second question, because I think this is now clear. In the FReET model files, again about FReET, are the distribution function for each parameter already the best options, considering practical aspects for concrete degradation mechanism?
Okay. So maybe some user knows already FReET or documentation of FReET. So my colleague Professor Tepli and his team, they did really very big effort to combine many analytical phenomenological model, and they also recommended there was a recommended probability distributions and also recommended values of the some parameters, right? And well, if user knows something better, he or she can apply this something better, right? But we, let's say, produce some default parameters for FReET to make user, let's say, better living, because usually in case of degradation, not so much is known. Okay.
Yeah, thank you, Dragoš. I don't see any more questions. Maybe also check, because there is also a Q&A section, so somebody might ask the question in the Q&A. Okay, there is nothing in the Q&A. So with this, I would like to thank you, Drahomir, and also thanks to all the participants. And I'm also stopping the recording now.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.